Let me first introduce the setup. So the setup is the following. I take a fibration. So let me call F from X to B. For me, fibration today means a holomorphic, proper, surjective map with 5 connected fibers. So this is a fibration. I assume that the base dimension for simplicity is 1, and the dimension of the total space will be n, and the dimension of the fiber is bigger or equal than 2. These numbers are important because there is a huge literature when the dimension of the fiber is 1, the problem of fiber surfaces. I will only touch a bit during the seminar, but only a quick touch. What does it mean to study a fibration? A fibration, in this case, you can think something like that, no? You have your curve B, you have B, here is the fiber, FB, and here you assume for the rest of this talk, and again, it is a way to simplify the talk, that FB, the general the fiber, is semi-stable, stable. So I will write SS, which means normal crossing singularities and reduced. In particular, there are no multiple fibers, and I mean to grasp what can happen on some, let me call, bad value, B0, you can have something like that, no? Where the whole fiber splits, but in a very good way, the best way you can imagine. These are, is not actually, for most of the theorem, is not so, necessary, but makes things easier. Otherwise, you can use the famous semi-stable reduction theorem by Knudsen, Manford, Sendona, and others of the 73. And you apply, in a certain sense, barely this theorem if you don't have this situation, for what I'm telling you. What does it mean to study object like this? It means the following. You want to relate some invariants. For example, you take the geometrical genus of the fiber, which is constant number, is the dimension of the space of the global section of the canonical divisor, for example. You have what we call the irregularity of the fiber, for example, which is the dimension of the, let me say H0, better to write like that, the dimension of the space of regular one-fourths, of what in the case of curves theory are the abelian differentials. Okay, and you want to relate object numbers like this one to the ones of the global, of the total space, in order to, in a certain sense, to say, for example, if the variety X is of the general type, everybody of you, I guess, knows that it can admit only certain kind of fibers. But at the end of the day, all these results comes from the interplay between the invariance of fibers and the invariant of the total space. And we will be focused mostly on our object today, to understand the first word of the title, Fujita's decomposition. We will be concentrated on the following sheaf. I guess, but interrupt me, all of you knows the relative canonical sheaf, which is, okay, if you want to see as a divisor, is the shift given by the canonical divisors minus the pullback of the canonical divisor from the base. And what we do, what we will study, and I will tell you why I am interested to study this, is the F lower star of the relative canonical sheaf. Okay, this is the object of study today. Why? Because this, well, first of all, why it is important, this object. Let me try to give a, let me say, a motivation to say why this is important. If I should say quickly why this is important. So let me put here, because I will then tell you, send you the slides. This is important because you have to think that F lower star omega x b, its fibers over a point small b inside the curve b is the space of the total section of the canonical sheaf of the base. So essentially, you have to arrange all these vector spaces, no, this one. Clearly, for some people, what I'm saying now is trivial, but is a way to control how to arrange this union, because you have a natural map of X, actually often is rational only, in the projectivization, I mean the broadening, the proj of F lower star omega xb, which clearly I have not told you, I have forgotten to say that it is known by Fujita that it is a locally free sheaf. Okay, you have to study this map. It's a device, a technical device to study the fibration F. In a certain sense, this is the analog, let me say, of what the canonical model is for a variety. That's why to know this object, to know F lower star of omega xb is important. Okay, that's why we are interested in ampleness or semi-ampleness, semi-positiveness of this sheaf. And I guess that this should be accepted for all of you, I guess. So what is the famous, should say, Fujita's decomposition theorem? Actually, as always in the nice facts, you have two decompositions. Well, the first that I only quote decomposition is the following. F lower star omega xb is a direct sum of some trivial copy, of some copies of the trivial sheaf over B, direct sum a vector bundle E, where the only properties for us is that the H1 of E is 0. E is not, in general, ample. Let me say, this part, I don't want to enter too much on this decomposition, but to grasp even in this case the importance quickly of this decomposition is the following. Once you want to study fibration and fibers, what you can do, what you can imagine to do. No? So you have your fiber, your FB, then you start with some cycles here. And what you do? Well, clearly the dimension now is 1 on this basis B, but you think that the real dimension is 2, so you move outside the fiber this cycle and you'll be back, no? Let me say you do homologically this kind of games. And what you call the invariant part, so the cycle, let me say the geometry that you have on the fiber because is inside the big variety, essentially in a very sloppy way, is related to this decomposition, let me say. So you start to grasp, this is the only, can I say, my intention in this first 15 minutes, you only grasp the importance of this shift. Let me say this rule, that invariant part, I mean, these two are, if you look at the dually, they are the same on the homology. They are related to this part of the decomposition. So now we start to enter instead in the important decomposition, the second one, which is really the decomposition we are working on. So the second decomposition is like that. You have a piece U and a piece A, where A is ample. The ample, well, first, guys, the rank of this sheaf is clearly equal to the arithmetical genus of the fiber, right? As I told you, if you take a point B, the stalk is the full set, the full vector space of top forms on F. But the decomposition, the second Fujita, the first step is ample. The second one is what we call is unitary flat. Now I understand that these words does not mean, well, I don't know if people knows the meaning of this notion. Quickly, this unitary flat is, there is a theory, let me call very general framework. Actually, it is the framework of local system, where you have three different, let me say, categories. I quickly recall for you. So there is an equivalence of categories between unitary, let me say unitary, that's why you, no? Unitary flat vector bundles. This is one. Two, local system. I will recall you the meaning of these words, local system. And three, monodromy representation. Of what? Indeed, of the first fundamental group of B in some vector space V. Okay? You have, so what is a unitary flat vector bundles? A flat vector bundle, let me call, when I say flat, means that you have a connection on U such that it has zero curvature. In a certain sense, it's like a differential geometry notion, which means this. The connection you repeat is zero. This means flat, unitary flat. Local system, so this is I. Local system means what the easiest thing you can imagine is, so let me call V. I usually double one of the lines, not like this. This is not V, it's V with this second line. V is a local system, means that is a sheaf of vector spaces that is locally constant. So, to have an idea, when you think to locally free sheaves, or how do you call, vector bundles, you have what you call the cocycle conditions. Now you relate the section and S alpha equal G alpha beta S beta, and all of you knows that knowing the G alpha beta gives an element in H1. of a certain covering, and O star, etc., etc. No, or GL, sorry, GL O star. I mean, you have these maps. In the case of local system, essentially these are constant. So constant matrices. Once you know how to change on one point, you know in a neighborhood. These usually are functions when you are on a vector bundle side. For local system, they are constant matrices. So on each point, you have a vector space, but let me say if you move a bit, it's the same vector space. And the monodromy representation 3, well, this is actually is only what you can imagine, is an homomorphism, a group homomorphism actually, from P, the first fundamental group, to the vector space D, homomorphism. Why I recall this? Because you could say, okay, what does we care about? The point is that this unitary flat has another interpretation. This is the big theory behind, which I guess some of you could be interested in, which is the semiampleness condition. So in this sense, U is unitary, flat. Let me say with, this is the new fact, finite monodromy. This is equivalent to U is semiample. What does it mean, semiample? It has that there exists a multiple of the tautological sheaf proj U, which is generated, is base point free. Base point free. Okay, how do now for young people, how do you translate all the notions you know, ampleness, naffness, semiampleness, when you know only for divisors and line bundles? How can you go to vector bundles? You take the proj, you have the tautological sheaf, and for the tautological sheaf, the same condition must hold. So in this case, U is semiample, means that the tautological sheaf is semiample, which means that there is a power of it which is base point free. So there was a very long-standing conjecture which said by Fujita. So now I move from here. Fujita's conjecture in the end, one of the many, but however, Fujita's, let's say, claim, to relax a bit, no? Fujita's claim is that U, in his second decomposition, then I will tell you a bit of history. This U is semiample. But now, guys, why this is important, however, I have told you a bit, but if it were true, this would have meant that up to base change, you could have had situation very nice. I mean, you could have done base change of your curve B. I will tell you something later. A standard base change, a Galois base change. And here on the new variety, you would have seen a lot of geometry. Means that new map. You could have studied this up to base change, the semiampleness of U means you have a lot, let me say, of morphism to other variety. And as you know, as soon as you have morphism, you can know a lot of your variety. At the end of the day, how can you know a variety? By slicing or by morphisms, no? So this would have been very important. Okay, are there any question for the moment?
Yes.
Yeah.
All your varieties are assumed to be over complex number.
Yeah, sorry. You are totally right. Sorry.
Yes.
I am over C. Yes. Okay. This is, I repeat my set. No, you are right. So if I have here, my setup is over C, semi-stable fibrations, and smooth varieties. Okay. This is why I said you before, I am, let me say, before 2010, more or less. You will see why this number, more or less. But in this sense, what I'm saying could have been done before. So now I have clarified this point. And let me say why how can you understand a bit semiampleness? I can tell you I can do an exercise for you, which is suppose.
Sorry, I still have a question. In the previous page, you wrote rank equals the arithmetic genus of fiber. Rank of which bundle?
The rank, no, the rank of F lower star, this one, no? This rank, this is the dimension of H0 F. How do you denote the canonical shift? What I call P, the arithmetical genus of the fiber.
Okay, thanks.
Okay? Possibly people who knows fibration theory for surfaces would recover this is the genus of the fiber. Now, I want to show you one thing, which is the following. Suppose you know.
Francesco, just put it a bit down. Exactly. Good, thanks.
So you are right. Suppose you know that there exists a Galois cover. So B prime divide G equal B. Let me call, well, I don't call for the moment. I have our X. We have our X prime. And suppose that for this Galois cover, pi upper star of U becomes trivial, which is essentially the notion of semiampleness. So it's something like B prime times P to the rank -1. R now is the rank of U, which in general is less than this, no? Suppose semiampleness in the sense of the, let me say, representation theory. Why? How can you see, only to you to understand why it is important to ask these semiampleness properties? How can we see, let me say, semiampleness? This is easy. That's why I can show you quickly. Because if this happens, take a linear form, take a point P, inside PR -1, and a linear form L, such that L, let me write like that, L equals 0, intersection the orbit of P is empty. Clearly here, the assumption, the finiteness assumptions here for semiampleness exists a Galois a finite here, Galois cover. So in this case, to have a linear form which does not intersect a finite orbit is possible, but I mean, if otherwise, no. But suppose we are in the finite case, in what I will call for the rest of the seminar in the algebraic case, then what I can do now I can take the following form, let me call T, which is the product of G upper star of this form L, where G is in G. G is the Galois group acting, no? Clearly, this is a G invariant, and degree of T is equal to the cardinality of the group G. Let's call for a moment A. It is G invariant, so it passes to the quotient, and what happened? It happened that T, I call T hat the same form at the quotient of P, is different from 0. So I have found what? A multiple, let me say now, a multiple of the tautological sheaf, actually a multiple of this, which is generated. Actually, the fact that I know even this multiple, the multiple is exactly 8 times the tautological sheaf of U. That is the importance for the algebraicity. So if the Fujita conjecture were true, you would have very nice situation in order to study this part of the, let me say, this piece of the decomposition, of the push forward of the relative canonical sheaf. But in 2013, in a series of papers, but actually in a paper, Fabrizio Catanese and let me say, sorry, because with names I'm very terrible. It was Michael Deckelweier. They in a paper in honor of the 70s of Kawamata, Jiro Kawamata, they disproved the Fujita's claim. So show that U is not always, let me say, I would say algebraic in some sense, let's say correctly, semiample. So the gain to pull back via a Galois cover and try to study the new variety to have information on the former one usually does not work. But this makes very important now to understand when it is semiample. So my, let me say, aim in this is why this long presentation, my aim is study conditions such that U is semiample. Okay? I think that this is, as you see, the hypothesis, guys, are, are last century hypotheses in the end. So I understand that for young people should be better to phrase this problem in a, let me say, larger category where you have some KLT singularities and so on, and I agree. But still, to understand when this is true, now is a problem. In a certain sense, if Fujita were right, this wouldn't be any problem. It would have been always. So which are the conditions to answer semiampleness? So to say that you have a lot of algebraic subvariety hidden inside X that you can study. Okay, that is let me say the problem. To answer the problem, so to describe, so problem, the problem now, I guess, should be clear for everybody, and let me know if it is not true. Problem, study, let me say, study U and semiampleness conditions, okay? Are you all in touch? The problem should be at least well defined. So, to study this, prepare yourself. I have to introduce the main charter of today, and I will do with a slides that I have prepared before, not to waste time, but I will be very, very slow to comment it. So I will put here, look, don't be, don't go to take a coffee now, but clearly is not sent, or yes, okay. So who will be the main charter of today? Because at a certain point, I will have to quote people who have studied the problem before. But let me say that the problem has been studied only, or at least mostly, for surface theory. The main charter will be this guy, that for the moment is nothing for you, but his name is dn-1 and will be a local system. Okay, this is my tool. Actually, I should ask. This is a joint work with Luca joint. That is the first name I have to remind you, Luca Rizzi. Our main tool is this local system. How can we, and then I will tell you some theorems on this local system. You see? Okay. So how can we construct this local system? Let me comment. There are two ways. Now I want you to be concentrated on your fiber, so on the picture I did at the beginning, and on the fiber you have his own top forms are n-1 dimensional object forms, while the volume forms on the big variety are n forms. And there is an interplay between n forms on the full variety with n-1 forms on the fibers. And this is easy. It's the easy part. It's just restriction. But there is also another way to reach n-1 forms on the fibers, coming from, loosely speaking, n-1 forms on the total space. So these two ways combine to give this local system. How can we describe it? The description, guys, actually is quite easy, because you start with the only sequence you can think about. I mean, the co-normal sequence of the fibration, no? So you have the pullback of the canonical sheaf of the base. These is a curve. In this case, the assumption of curve is important. These are the one forms on X and the quotient. Now, our assumption of semi-stability gives torsion freeness of the quotient. That's why I need this hypothesis here. But I mean, okay, let's go on. Once you have that, you can consider a lot of standard sequence that you can imagine. You do the wage, the suitable wage of this sequence. And actually, we only need to consider two. The wage n-1 sequence. So I can take, you see the numbers. Okay, these are n-1, which comes from the wage n-1 of this. And these sheaves are the n-1 forms on the total space. And the wage n, here you do the wage n, and here the wage n-1. The wage n of this object is nice because essentially this sheaf is the sheaf of the total volume forms, except on the scheme of critical points. And as you know, even in this case, the assumption of semi-stability makes things easier. But now, by definition, what you do now, instead of this sequence, you take their own resolution via the RAM complex. I didn't want to write all this huge diagram that goes on, which is a resolution by the operator D, how do you call the exterior differential. But you take these sequences, you solve using the RAM resolution, and then you push forward on the base. This is the game. It's written in the paper. I guess that if people knows the RAM resolution, it's very easy to be seen. In the end, when you know where you want to arrive, you want to arrive to n-1 forms on fibers. So, and then you take this object. What is this object? You see, it's something very easy. Essentially, you could look to the push forward of this sequence, and I guess you can see in your mind. And you should have a morphism from F lower star of this sheaf in R1 lower star of this sheaf. But doing all the computations, you can check, and it's doable, that you can consider a more refined method. Instead of going on, let me say, this sheaf, you go in something that is still on the big variety. You take the closed, here this D is the point, the closed holomorphic forms, n-1 holomorphic forms. And you have a cokernel, the standard cokernel. Instead of the one I have said before, you take the cokernel of the push forward of the sheaf, so this, to the push forward of the n-1 forms closed. And what is this D n-1? Actually, this is a sheaf of forms which represent the forms on the fibers which are liftable to closed holomorphic forms on the, I call, global object X. So you have to imagine that you have these forms on the fibers, the one that you can lift to forms on the ambient space which are closed. Okay, and in fact, you can also see inside the relative canonical sheaf via closed relative differential n-1 forms. But I wanted you to see before on the total variety, on the total object, on X. On X, you can define a sheaf. What is this sheaf? Are the forms on the fibers that you can lift to closed holomorphic forms on X. You will see in a moment why this object is important. But are there any questions, guys? No problem to ask, because I understand that this way to explain things could create some problems because of numbers, but essentially you take the RAM resolution, you push forward, you check obviously Snake's lemma and so on, blah, 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 and you find this object. Let me comment a bit because this silence is a bit worrying. So I comment a bit. If you want, what you do is the following. You take the inclusion B0 inside B, B0 are the regular points or values of the fibration Fx over B. So the fiber over B0 are very good, are smooth. And you can interpret, now you pull back your object. So you do J star of this main charter. And what is this? Clearly is a theorem, but this is the largest local system, contained in F lower star omega n minus 1 xb restricted to the regular set. And once you do that, and I guess again is a theorem, you do a very non-trivial game, because you show, but this honestly I will tell you, the people I have learned from whom I have learned how to do, you show that this you go now again over the total curve B, and you can prove that actually this is exactly the same. And so by this game, which is not easy and requires clearly here the assumption of singularities has its own importance, however, you can prove that another interpretation of this main chart of the main object is the largest local system, obviously inside F lower star omega n minus 1 xb. Okay? If you don't have understood anything for the moment about this definition of the n, you can take this, and this is sufficient to understand the rest. You have a local system, so means that over every point B, you have a vector space given by certain global section. So you have your point B, in B, you have D n minus 1b, which is a vector subspace of the space of the global section. And in a certain sense, this vector space is well defined in a neighborhood. It's the same, let me say, if you move a bit. Why this is important, this object? Clearly, because from all the sequence I've shown you, but otherwise take for the moment for granted, because it's purely linear algebra, because this shift, you have an inclusion in the relative canonical shift, in the push forward of the relative canonical shift. And the first theorem, let's say Rizzi Zucconi, because honestly, I guess that people like the lineage, etc., knows these things even better. But I have never shown a proof in the general case. I never shown, and I guess that is important to know, because let me say the unitary flat part of the second Fujita decomposition is exactly the local system I have introduced. Obviously, I have to tensor by OB, because otherwise the local system is not an OB module, no? So this is a theorem. Let me comment here where I've learned, let me say, the setup, etc. And you can understand that, however, I have not answered to the question how to study the semiampleness of D, but at least I have introduced an object, an easier one, because it's a local system, which can help to study. There are a series of papers, but essentially are Fabrizio, Catanese, and I have here, sorry, the man I want to quote correctly and very well, sorry a moment, and Michael Detweiler, Catanese, Detweiler, well, let me write correctly, Catanese, Detweiler, who made a very nice exposition, and actually they provide the only known proof of the second Fujita decomposition, because Fujita, let's say, claimed to have this, but never provided details. So if you want a very clear exposition, is in a paper by Fabrizio and Michael, 2013. From this point onward, a lot of work has been done to study this situation in the case that I don't want to treat the case n equal to, so the surface case, because before giving other theorems I have on these topics, I want to introduce the other, let me say, in a certain sense, minor character of today, and then I can give you very quickly the basic theorems. I have now my second slide. Please don't be shocked. The second line is this. There is an important splitting theorem which enables to study a bit my Dn. How can I, what is the content of this theorem? Again, start from the standard sequence you can imagine, and you start to do, you see, the theorem resolution of it. Here you have the relative theorem. Okay? If you do this and you consider the kernel, so you add to the standard ladder the third one, where you have the kernel. Here you have the one forms which are closed. Here you have the relative one forms which are closed. And here you have a kernel. Okay, don't worry about that. Then you see, we can prove, this is a theorem, that actually there is a sequence like that. So the theorem, I didn't state as a theorem, but it is a theorem. There is a sequence like that, and the co-kernel splits. That is to say, inside the push forward of the closed.
Sorry, we can't see that part. Yeah. Thanks.
Sorry. The push forward of the closed forms splits, and this is again, D is again a local system. And again, the idea is the same. They are the one forms on the fiber which leads to closed one form on the total ambient space. Okay, essentially it's the same idea, but here you have this important splitting. And now is the moment to say the other piece of information about the history very quickly before my last results, which in the case n equal 2, there is a very nice thesis, Sara Torelli, PhD thesis, under the supervision of Gianpietro Pirola, and some papers by Torelli, Sara, and Pirola and Torelli. I prefer young people, and I usually put young before, but here the alphabetic order is PT, quindi Pirola, Torelli, and in 2020, where they did exactly the splitting theorem. So they have the most important theorem of the thesis in the end is this splitting theorem. And I don't want to enter all the, let me say, geography and geometry that you can extract from this kind of results, but only quickly I can tell you what's the content of this theory and the fibration theory. You know, whenever you do the reduction, no, on the residue fields, you obtain a subspace in the case of dimension 2 of, but okay, it's the same. Okay, and you obtain a subcanonical linear series. And so you know, you can relate the geometry of a hyperelliptic curve where you have subcanonical map induced, now the G12, tricanonical induced by the G13. I mean, you have all the geometry you can imagine on a curve, because in the case n equal 2, the dimension of the fiber is 1. And so you can relate all these, you can try to understand what kind of subcanonical linear series U tensor KB gives on your general surface. And you easily understand that to relate this number, this dimension, to the genus of the fiber, provide you a lot of information to study the full variety which hosts the fibrations, for example. So there is a huge theory where is plenty of people, and let me quote some of them, is Paola Stoppino and Miguel Angel Barca and Juan Carlos Naranjo and I don't remember the name, sorry, Favale and others, who arrange these numbers to the geometry of the surface. But the new fact of vibration theory in the last, in my opinion, the most important in the last years is exactly the splitting theorem in the case n equal 2 by Sara and Giampietro. I don't know why they publish not in a very, very top journal, but I don't want to enter referee minds. So how, now let me give quickly the tool to have some, I mean, some other results on our semiample, on our unitary flat vector bundle. So I have to introduce the Massey products very quickly. I have another slide, sorry. Massey products. As I told you, these objects, if you look fiber-wise, are n-1 forms. If you look on the ambient variety, essentially are volume forms in some sense. And this reflects in two operations, indeed, that you can do. We have a local system, D, of closed one forms. So if you do the wage n of D, and everything is over B, you goes very, very quickly, you see, in the wage n F flower star of the closed one forms. But this object goes inside the push forward or the canonical of the variety. So this n is, let me say, the right number to study object here. And to go to the relative canonical sheaf, you have only to tensorialize by the tangent sheaf of the base. This is what in differential geometry is essentially the Lie contraction. So you start with the spatial local system, you do the wage n, you have n forms essentially, actually you have a family of n forms, but you do the Lie contraction and you obtain relative canonical top forms. But you can also do the wage n-1. In this case, you are more related to the dimension of the fiber. And doing the same game, again, you finish, you enter, let me say, in the same sheaf. So how can you relate this, knowing that there is a third object? Don't forget the theorem I gave you, this object, no? How can I relate D, the n, well, you know. Okay, this is the idea. And to do that, I have to use these two homomorphisms, and let me give you another. Sorry, I go a bit quickly, but don't be worried. This is very easy. This is easy. These are the two maps I have described before. At the level of n forms, at the level of n-1 forms. So what you do? What is the technique? And let's see the flesh, of the argument. You take your local system D of 1 forms. These objects on an open set A, on an open set of B are what? These are families of 1 form, if you see on the total space. And if you do the wage n-1 of them, you obtain object like that. Is the same argument that you are doing here. And this, let me say, this arrow. And so starting from exactly dimension n, so this means that you have to consider varieties, fibers, which are, let me say, very hyperbolic with a lot of 1 forms at least, okay? You can construct global forms, omega I, which are of this sheaf. But you can do the other contraction. So you can take your volume forms, you do the recontractions, and you obtain again, let me say, something that on the fiber, on each fiber, is an n-1 form, but coming from a volume form. I don't know if you grasp at least the game. You start with the dimension of fiber plus 1 forms that over the cylindrical, you have this A, you think over the cylinder, and these eta I are forms that restricts to closed 1 form. There are closed 1 forms here, which restricts to 1 forms on each fiber. So you can do these two linear operations, waging n or doing wage n and recontraction. But at the end, on every B, you land in the canonical sheaf of the fibers. How are these two related? How are, in a certain sense, this volume form omega is produced by these n volume forms on fibers? Which is the relation? It's called Massey product of this. Well, the basic notion here that is a long-standing, is that this notion of Massey products has a long history, but I don't want to enter in it. But the proper notion that I want you to grasp is, okay, if I do this game, take these n forms which are closed on the cylinder, I do the wage n, I have a volume form, I restrict, I obtain nothing else of what I would have obtained only with the n-1 forms omega I. So if my forms omega belongs to the space generated by these n forms, then I say Massey trivial. I hope you have. Did you follow this point? Did you understand what is going on here? I have, you have very quickly. I know that I'm going run out of time, but think a situation like this one for a moment, where x are the variables on the fibers, and t is the variables on B. And these are 1 forms, You can do wage n, so you can take, for example, eta 1 xt, wage eta n-1 xt, and restrict, for example, to t equals 0 is something, this restriction is something, or you can take the full volume form, eta 1 xt, wage eta n plus 1, xt, and restrict equals 0. It's like when you do at the first year the external product, how do you call it? Now, do you obtain something new? This form, which is inside H0 omega F0, belongs to the space generated by this one. These are, you can think to this as a kind of direction. And is this a kind of orthogonal direction or not to the previous one, to the one you have obtained, to the n you have obtained by wedging n minus 1 among them? Okay. If not, you say that the space, the vector space generated by eta 1, eta 2, eta n is Massey trivial. Why I tell you that? Because actually this gives us the theorem I want to explain you, which is this. Sorry, so if I have W inside gamma A D, I have the representation associated to W. So I have rho W, P1 B inside U rank of W C. You have the kernel, HW is the kernel of rho W. And then you can take all these subgroup and you have a theorem, the first theorem, which show you the rich geometry behind. Let's say that if you have an open subset B and F a semi-stable fibration over B, to say that W is Massey trivial, so you have a lot of forms, but when you wedge, at a certain point you obtain nothing, let me say new, the wedge of these one forms does not create new forms, okay, then up to base change, I mean, exists a base change, let me say xk, x, b, which is b divided k, bk, sorry, bk divided k, and exist in hk such that xk goes to y, and y is normal of general type, and w is inside hk star h0 omega 1y. Why this is important? As I told you, up to base change, you provide your variety, not x, but let me say an easy base change, with a lot of structure coming from new varieties, which are related to this local system. Okay, this is one result. And for people who knows, this is a generalization of Castelnuovo de Franchi's theorem, but quite more general. Now, let me finish to answer the previous question. How can I answer to some problem about semiampleness? And I am really close to finish, guys, sorry. Instead of W, now take what we call the local system generated by W. So any local system has its own, let me say, representation. I mean, you have the local system D, I have introduced before, of the one forms on fibers which lift to global closed D forms. This is a local system, it has its own representation. Then you know that you can take the image of this, it acts over, obviously, D, and you can take your sublocal system, which is not W, but is W, and all is, let me say, translated by the group G. This is a local system because it is invariant by G, and when it is Massey trivial generated, when, let me say, the new direction does not exist, how can I say, when you can control the top forms on fibers with one forms on fibers, this is the essential meaning, then the associated monodromy group is finite. And we have also a description of this situation where we understand perfectly how this local system is done. I mean, we have the previous variety Y. This is the previous variety we had. And here we have the inclusion. And actually now we have an equality. So W is equal. Let me say full description in the case of Massey trivial generated. And finally, and this is the end of my talk, is this. Assume that the global D, the splitting local system, is Massey trivial generated, and waging, you obtain the surjection with the main character of this, in the end of this game, the new one. Then Dn has finite monodromy. That means that U is semiample. So in some sense, these results gives a partial answer to when when the unitary flat of the second Fujita decomposition is semiample. At least in one case we can tell when this part, the local system which gives U, comes from one forms, let me say. And then I have an application, there are several actually, but at least one, which says the following, that if I have a fibration where each fiber has an involution such that the quotient variety is not, has geometrical genus equals 0, and D is generated by anti-invariant one forms, then this is a case where D is Massey trivial generated. So the theory is not empty, and essentially this is the generalization of the theory of hyperelliptic fibrations. This, in the case of surfaces, correspond to the case where you have an hyperelliptic curve and D is generated by invariant one forms. So in this sense, is a generalization of a famous theorem on surface theory, which says F hyperelliptic, and I don't remember, there is another hypothesis to be honest, but then, however, F lower star omega X S in this case, no? B is semiample. No, this was Shao theorem. But however, what is important here to finish is that we have some partial results clearly based on the theory of the one forms essentially, but this part is really new in some sense, has never been studied, and there is a lot of things to do. If you are interested, I will go on. Otherwise, I stop a moment and I wait for questions.